So this is joint work with Chiranjeev. I guess this is slightly different flavor from purely linear algebra, but it's connected enough that I think it can fit into this conference. It's also nice to talk at 2 o'clock because that's my prime nap time, and so I've not been known to nap when I'm talking. So that's actually saves one person. But okay, so let me introduce a problem. Okay, and this works too. Okay, excellent. Okay, so I'm going to start with something which is a special case of what we're going to do, and is something that's very familiar to all of you. And then when I go to the general case, it will be clear what I'm generalizing. So k-means clustering. This is also with a view to set up some notation that I'll use throughout the talk. I'll try to avoid too much notation, but there's some. There are n data points. I'm thinking of these as columns of a matrix. So A dot 1 is the first column and so on. So the n data points in D space, and you would like to k cluster them. That's the k-means problem. But perhaps in a departure from TCS k-means, the usual k-means that comes up in statistics and so on is that there is a ground truth clustering. If it's Gaussian mixtures, it may be the clustering generated by the Gaussians, but we are not assuming any stochastic model. But there is some ground truth clustering which has centers M1 through Mk, M for means, and we would like to find that one, that ground truth clustering. It's not always true that you can find it, and in fact we want to know deterministic conditions on the ground truth so that Lloyd's algorithm in particular finds it with a good start. Okay? I won't be very specific about this, but I will be specific about the conditions. So this particular question, what are the conditions that are sufficient to ensure that we find the ground truth clustering? One set was found by somewhat older papers, like 10 years old papers of mine with Kumar, and an improvement or a simplification due to this paper of HT and Sefet. And here is the condition, which is very simply stated, the simplified condition. We want pairs of different centers to be at least a certain distance apart, and I'm going to express the distance in a somewhat peculiar way perhaps. One is there's a constant depending only on k and the minimum weight of a cluster. That's got to be polynomial in k. We'll call that C. But the second term is interesting. This is the spectral norm of A minus P. I have to tell you what P is, divided by root n. So you can think of it as the mean squared distance, maximum mean squared distance in one direction. That's spectral norm. But mean squared is divided by n. When you take the square root, you divide by root n. Okay? Where P is a matrix constructed of the centers of each of the data points, cluster centers of each of the data points. Each Pj is at one of the m's. Each Pj is one of the m's, right? Different m for depending on which cluster you belong to. Okay. Now, I won't be able to describe to you in detail this proof. I don't really want to. All I want to tell you is that there is a deterministic condition which depends on spectral norm that guarantees that Lloyd's finds the optimal clustering, the ground truth clustering. The proof is not simple, but just a flavor of the result rather than the exact result is what you need to remember. The result is, at that point, the result qualitatively subsumed all things that you could do. Qualitatively meaning the factors of k were not optimal, but what you could do with Gaussian mixtures, planted partition, etc. Okay, so I'm going to take this problem. I'm going to view this as learning a latent polytope problem. In a way, it seems like a perverse rewording of something you know, clustering, but with a point I'll make. So here I'm going to pose the same clustering problem as a polytope problem. So there's a latent polytope k with vertices which are cluster centers. So the m's or the vertices of k, the k cluster, little k cluster centers. Each data point, imagine, is generated by picking a cluster center that it belongs to or a cluster it belongs to. This is the ground truth generation by the hidden hand that I don't see, right? So it picks Pj equal to vertex of k and then perturbs it to give you Aj. Okay? You think of it as a perturbation, perturbs it to give you Aj. Aj is given to you, Pj is not. So the other point I want to make is that individual perturbations can be very large. So in the Gaussian mixture case, quickly, if you had standard deviation sigma, since you're sitting in d dimensions, points are at distance about root d times sigma from the center. Root d is very large compared to the dimensions I'm going to talk about. However, the spectral norm is just sigma for Gaussian mixtures. Okay? So it's missing a factor of root d, right? The spectral norm is much smaller than the distances of points from the centers. That's an important point. So no data point lies in k because it's a measure 0 set. In fact, no data point lies anywhere near k, right? And yet your objective is to find k given aj. Okay, that's what we want to do. In the clustering problem, this is an old result. Now let's generalize it. At the moment, it looks like a generalization for the sake of a generalization, but it has quite a point, and I'll make that in a minute. So I'm going to generalize it in the slide and then tell you why I'm doing it very briefly. Now, the generalization is simply stated. Each data point now doesn't belong purely to one cluster, but belongs to a convex combination of clusters, or if you will, it belongs fractionally to many clusters. You can think of it as soft clustering. So another way to say the same thing is Pj, the latent point, used to be a cluster center, and now I'm going to let it be a convex, any convex combination of cluster centers. So Pj is any point in K. K is the convex, all of those things. Pj is any point in K, and you still think of Aj as a perturbation of Pj, and only the spectral norm bounded. Okay? So I hope the generalization is clear. It's not clear why I'm doing it, and I'm going to make that point why I'm doing it in a brief slide here. Why the generalization? And this will, the detailed discussion of this will be postponed till the end, but several important unsupervised learning problems of precisely this generalization. Topic modeling is a good example. If each document is just on a single topic, it would be the pure clustering problem, but that's not as useful as the traditional model of topic modeling, which is each document is on a mixture of topics. That's precisely this general problem. So it's less analyzed or mixed community models, which are models that model community relationships, that people knowing each other, and each person belonging to a mixture of communities is more interesting than saying they belong purely to one. You know, many of you know the stochastic block model. It's a pure model where each data point belongs to a single block. So that's the simple clustering problem, if you will. Okay? Now, that's the problem we are going to look at. We are going to look at this mixed membership clustering. So every data point belongs fractionally to different clusters. Okay? That's the point we want to look at. It turns out I'm able to tell you the starting idea and also the complete proof of that in the next couple of slides. I, of course, won't be able to tell you the proof of the whole thing, but the starting idea is simple, and I hope I get that across. The idea is subset, what we called subset smoothing. That's the name we gave to the following technique that I'll describe. Now, intuitively, we always have to assume that sufficiently many Pj lie near each vertex of K. So K is a convex set. You want to find the vertices of K. Those are the cluster centers, if you will. Now, if all your Pj lay in the middle of the simplex, there's nothing you can say about the corners. So you better have enough latent point at least near the corners, right, for you to be able to say something. Now, in the traditional clustering, the analogous assumption is each cluster has a weight at least a certain amount. If you have a weight going to 0 of a cluster, you don't have to hope to find it, right? So we assume, analogous to that, we assume that for each vertex of K, each of those pure clusters, there are at least a delta fraction of points which are near that vertex, Pj near the vertex. Aj or not, the data points are anywhere else, right? Not near, very close to the vertex. So here's theorem 0. This is the theorem I'm going to hope to prove to you in the next slide or so. The theorem says the following. I'm trying to find the vertices of K. I can just think of it as trying to find K, because K is just a polytope. Once I find the vertices, I have it. Okay? But I claim here's an object. K is not data determined. It depends on latent things, right? Here's a thing that's purely data determined, K prime, which is I'm take the convex hull of n choose delta n points. each of those points is an average of aj, average just means coordinate-wise average, belonging to a delta n subset. So I take all delta n subsets of data. There are n data points. I take all delta n subsets, take their average, and take the convex hull of these exponentially many points, and the claim is that's close to the original polytope you started with. Okay? So this would be useless except for the second part, and I'll come to that. So first part says that k prime is pretty close to k, but it's an exponential object, and so it doesn't seem useful to prove this theorem. But however, we'll see, and this is theorem 0, it's simple. We'll see that k prime, in fact, has a polynomial time optimization oracle. So you can get a hold of k prime in polynomial time in this sense. And we'll see that that's enough to get a hold of k. So why work with k prime is exponential, but data determined, right? Whereas k is not. K is what we are trying to get at. Any questions so far, or?
I think you'll show us like in a minute, but what's our notion of close here?
I'll show you what?
I think you'll show us probably like the next slide, but the notion of close is what for these polytopes?
This
close, like k prime equals about k.
I'll show you that.
You show us, yeah.
I'll show you both parts.
Okay.
Yeah.
So here you're saying something delta fraction or near the vertex.
Yeah.
Because you're taking this convex combination mixed membership thing. The previous assumption was not, it didn't have that. It was the spectral norms were close. Does that apply?
The previous assumption had that. Because the previous assumptions, in clustering, you always have parameters depending on the minimum weight of a cluster. For instance, the separation has to depend on the minimum weight of a cluster. Yeah. Another way of saying that is every cluster at least a certain weight, so that you get this separation is enough.
Yeah, the weight's fine, but the previous thing didn't have any assumption that any of the points were near. It just depended on the spectral norms being close.
No.
Is that correct? Or does that imply this?
No, but yes, in a way, yes. But the separation between cluster centers in the old papers depend on the WMIN. So the smaller the least cluster is, the more separation you need.
So if they're large clusters, they could overlap a lot.
If there are large clusters, they don't need to be quite so separated.
Okay. So does that imply something like this delta fraction, or?
Okay.
Or is this an incomparable?
Yes. So instead of the delta fraction, I could have said the following. I could have said the separation between the cluster centers depends on the fraction of points that lie close to this. That's how the old papers put it, right? So instead here I'm putting down delta explicitly, right? So is it clear? Yeah. So there is no new assumption per se. It's just analogs of old assumptions. Let's see. Any other questions? Okay. So let's prove this. Proof of theorem 0. So recap notation once more before you go into the proof. K is the original polytope. Pj are latent points. Latent means not given, but they are in K. Aj are data points which are perturbations of Pj, but they're very far. And K prime is this exponential object, and I like to prove they're equal, roughly. They're not equal, they're close. So each subset of delta n points has an average Pj which belongs to K. Individual Pj's belong to K. If you average many of them, they still belong to K. It's convex. And the average of Aj over delta n subsets is close to the average of Pj. That follows from spectral norm. I won't go through this proof, but the following is a simple fact, right? If you have spectral norm bounded by something, sigma, then if I take averages of large enough subsets, they are also bounded. Okay, that just follows from. You just get a large average by applying a minus p to a vector of ones, the indicator vector of the subset. So that's a simple fact. So each subset average of Aj is approximately in K. Each subset average of Pj is in K. Aj is close to Pj in average, only in average, not individually. And so this is true. So that says K prime is contained in K. You need the other side. Now there are delta n subsets of Pj close to each vertex, ensure. So there are basically averages sitting close to each vertex of K. and therefore k is a subset of k prime. Together we get this. So we got both parts, an equality, and optimization oracle is your job. So why is it that k prime has an optimization oracle, which is simple? What is k prime? K prime is a convex hull of averages of delta n subsets of data. Okay? So I want to claim that it has a very simple polynomial time optimization oracle. That's if I give you a linear.
Optimization oracle?
So that means that if I give you, I was just going to say, if you give you a linear function, you should be able to optimize the linear function over the convex set. A convex set is an optimization oracle if optimizing a linear function is polytime.
Finding minimum or maximum of the linear function.
Yeah, either way. Both. I mean. So why is it that I can optimize a linear function over k prime? So I want to maximize u dot x over k prime, which is the convex hull of all averages of delta n points. So it does have exponentially many vertices.
It's like exponentially many, but they're all linear combinations of.
Sorry?
I guess it has exponentially many vertices, but they're all linear combinations of like n delta n vertices. So I can write this.
No,
as-
it has n choose delta n vertices.
Yeah, so many vertices, but they're. Oh, I see. Yeah, so.
But they're all vertices, actually.
Yeah, okay.
So how do you find the average of delta n points which maximizes u dot x over all such choices, over all averages? Which subset of delta n points maximizes u dot x? You take the maximizing delta n points, right? You just organize the points in order of u dot x, the aj, and take the delta n points that have the highest value. Their average clearly is the highest average. So that you can do in polynomial time, right? So you just order the points in the linear function order and then take the maximum. So k prime is an exponential object, but it has a polynomial time optimization oracle. You can optimize any linear function over k prime in polytime by this very simple process. Okay. So that's theorem 0, and it should tell you perhaps it's possible to find k. My final objective is to find k. Perhaps it's possible to find k because what? I can find vertices of k prime by optimizing linear functions. Well, maybe they'll be close to vertices of k because of that k prime and k are close, and therefore I should be able to find vertices of k. This is the general idea. It's not so simple tablement. It will take us a bit of work to do. So let's see how to find one vertex of k first. And this is again something that's simpler than the general case, but it's harder than what I just showed you. I won't be able to show you the full proof of this, but it's not too difficult to find the first vertex of k. So we saw that k equals k prime roughly, and we can optimize over k prime. So the idea would be, let me optimize some linear function. Might as well pick a random one and optimize that random linear function over k prime, which I know how to do, right? So that's an optimization. Sorry?
We're gonna have to use that as random, though. If we want to pick a random one to get sort of like the important, to get the vertices of k, right?
We don't have to do a random one, that's true. I'm just taking a random one because it's going to illustrate a point.
Okay, but I mean, like, if we didn't do random ones, we could accidentally find like vertices of, or we could find vertices of k prime that aren't close to vertices of k.
We can find vertices of k prime,
Yeah.
but they obviously all of them will not be close to vertices of k.
Yeah.
K prime has exponentially many vertices.
Right. So is the hope that like if we do optimize a random linear function, those vertices that are the solution will be close to the vertices.
Okay, so you're asking me why I'm taking a random one.
Yeah.
I'll come to that.
Okay.
I mean, I hope to make that clear, but that's a question. Why random?
Okay.
Right. Yeah. So you pick a random u and optimize it over k prime, which we know how to do, and then it isn't y a vertex of k prime? The answer is yes. You optimized it, you get a vertex of k prime, all right. But isn't y close to a vertex of k? The answer is not automatic, right? K prime has many more vertices spread all over the facets of k, so it won't be necessarily. So many of the vertices of K prime will not be close to vertices of K. Okay. Yes or no? Now, if I apply Johnson-Lindenstrauss, it involves a root D factor. So basically, U has a very small component in the space of K. And what will happen is two vertices of K. So because U is random, with probability 1, every pair of vertices of K will have different values. That's one nice thing about picking random. You can guarantee that with high probability, they'll have different values. Okay? But the values can be very close, and they may be very close so that the Y you found, which is in K prime, will be close to a convex combination of vertices of K. So in fact, the Y can lie near a facet of K instead of a vertex, in lower dimensional face of K instead of a vertex. Okay? That's not a proof. I'm just giving you a slight hint because there can be ties. The major problem is any function U you pick, if it has ties for the optimal vertex of K, then you're in trouble, because the ties means that you cannot prove that you get an individual vertex of K. Okay? And you have to avoid ties. That's in fact most of the work. And it's not easy to avoid ties because your K-dimensional polytope, K small, is a very small part of the D-dimensional space. So in the D-dimensional space, this looks like a point. So there'll be a lot of ties. That's the intuitive point. Okay. Now, if I pick a random U in the span of K, K is in K dimensions, right? There are only K points. If I pick U in the span of K, then things are better. Okay. So then you get a root K factor instead of root. So I told you, ignore that for a minute. K is a small dimensional object in the big space, so it looks like just a single speck to a random U. But now if I pick U from this space itself, it doesn't look like a speck. There are distinctions, and that's what I would hope to do. But that's not so easy because you don't have K, you don't have its span. But there's a nice classical theorem. If you're already familiar with it, that's good. But if you're not, I do suggest this is a theorem about perturbation of eigenvalues, eigenvectors and singular vectors rather than eigenvalues and singular values.
So how do you get the symmetric or Hermitian matrix here?
So it's not Hermitian. There is a theorem. Vedin's extension of sine theta theorem gives you for unsymmetric matrices. So there is a theorem for singular vectors perturbation. Yeah, Vedin's theorem. Yeah. Yeah. So sine theta, the original name refers to symmetric matrices, that's right, but there's an extension to non-symmetric matrices.
This is not Davis Kahan?
No, that's Vedin has an extension to singular values. I don't know whether he uses AA transpose or he constructs matrix.
No, it is based on the proof of the sine theta theorem, but Vedin's theorem is.
I'm saying, but you have to get from from a non-symmetric matrix of which you take the singular value decomposition to reduce it to a symmetric matrix. There are two ways. Either you take AA transpose or you construct a matrix that's twice as big. So he uses one of those to get an SVD result from an eigenvector.
I think an online proof of sine theta theorem is hard because I don't know the proof, but maybe, yeah. So, that tells you that there is a data determined space, which is just the subspace U, which is the top SVD subspace of A, which is close to V. Close in the sense of angles. We won't again define angles between subspaces and all that, but close in that sense. And then for our proof, it turns out you can use that to show that it suffices to pick U at random from U, which I know how to handle. I know U, right? I have the data. I can find the K-dimensional subspace. I know U. So it's enough to pick that. Now, if we could take that U and maximize U dot x over K. Now, we cannot do that. We don't have K. And the vertices of K are assumed to be well separated. Then there will be a distinct max vertex in K. I just want the maximum and the second maximum not to be too close, because then I cannot argue anything. The game plan is to argue that any point of K far from this vertex will have a low value. So the game plan is to argue that in K, the distinction between first and second max is high enough so that in K prime, you get a vertex close to the vertex of K. Now, I've hardly given you the whole proof, but let me give you the theorem. This is theorem 1, a little bit harder than theorem 0, but it still only gives you one vertex. So it says that if we choose the random linear function u and optimize it over k prime, the solution is close to a vertex of k, provided the vertices of k are well separated.
Capital U was not the subspace of A. What's capital U? I'm sorry.
It was the SVD subspace of A, the matrix A.
Okay, now you're picking a random linear function in
A random vector u in big U. I just mean a random vector. And then take that u and maximize it over k prime, which we know how to do. And the theorem 1 says that will give you a vertex of k, one vertex. Okay, so we got one vertex, right? If you believe that. Can we just repeat this to get other vertices? The answer is no. Life is not that easy. I'll tell you why. Because again, without proof, it can be, and in fact in general will be, that if I take a random u even from this k-dimensional space and optimize it over k, there will be vertices for which the probability that that vertex is the maximum is exponentially small in k, because the angles can be very small. The angles can be exponentially small.
Like a very skinny diamond or something.
Yeah, they can be very skewed, long.
Can you explain a bit?
Or I think like I guess one bad example would be you have like a diamond that's very, very skinny. So
Yeah.
it's long in one direction.
If
short
you have
in
a
another.
long scalene
You'll
triangle.
only find the two end points. You'll never find these like close.
Right. Very good. So yeah, it's exponential in the dimension as well. So that this won't work. You cannot just pick random u's and repeat the process k times. So getting further vertices now, it's going to get vaguer because I won't be able to give you all the details, but I will give you the algorithm in full. How do we get the r plus first vertex having already found r vertices?
Why is that not, that's not taken care of with the assumptions you had before, these overlapped and so on assumptions, because it could be along the
So
line?
the assumptions only tell you that there is a fair distance separation between 2 points, right? But you can still have some angles very small.
So they could be along the line. or something.
It could be a long, thin thing relatively.
Yeah.
Why don't you just exclude that direction and take everything orthogonal to it?
I don't know that direction. I don't know k. I don't know which.
But you can look just in the space orthogonal to the one where you just picked one, right? And then next thing you explore the space orthogonal to it.
Okay, so it's not. So we will do something like that, but not that. Not orthogonal to the u. Orthogonal to the m's we found. That's what we'll do. Okay. So what we'll do is we've taken the first r plus 1 vectors, already found approximations to them, and I want to find the next one, next vertex. So we take a random u in the top k-dimensional SVD subspace of u. Will not quite work because that's the same problem that we mentioned already. It may just return one of the old ones because the new ones are exponentially unlikely to be optimal, right? What we do instead is pick a random u from u intersect null space of the already found m's, not the already found u's, but the already found m's. Okay. So now I'm going to put in one paragraph most of the paper, which is proving that this works is complicated. First of all, sine theta theorem does not apply to subspaces of this sort of nature, but we are able to prove a sort of a new sine theta theorem and use that and a bunch of other things to prove that the following algorithm works. And the punchline is the algorithm is very simple compared to the proof. So the proof I won't be able to tell you more, but I will tell you the algorithm. Okay? So the algorithm is just going to summarize what I said so far. So let's have a piece of notation which I didn't introduce before. A sub dot r is the average of aj, j belonging to r. Okay? Subset average. Okay? So first you do the subspace power iteration for log number of steps. Subspace power iteration is just the old method, standard method to find sort of the top singular space, and take the span of that. That's my v. I may have changed notation on you, pardon me, but v is defined here, not before. And you find vertices one at a time. You pick a random u from the k minus r dimensional subspace, which is the intersection of the null space of things you found. We haven't found m's, we have found a's. Null space of things you found intersected with this. And then you take the argmax of that. It is important to have the absolute value here. It's not true, algorithm won't work without the absolute value. You can get 0 still. Okay? By the way, you can do this with 2 linear programs. You maximize u dot this and maximize the minus of that. That gives you that. And the assertion is that's the end of the story. Simplicity, and the I won't analyze this, but the simplicity of the algorithm, including the fact that the subspace power iteration method can be made, is sparsity respecting, gives you an algorithm whose running time is k times the number of non-zeros in the original matrix A. Okay? I won't do the time analysis, but that's true. And in fact, I would, to my knowledge, this is even, there's no algorithm known, even for simple clustering, under these conditions, which runs in this much time, right? In general, in clustering, people mostly don't worry about sparsity, but it turns out these problems, topic modeling, mixed community membership, and stochastic block models, all these lead to sparse matrices. And it is important to cluster them in time respecting sparsity. And that can be done with this algorithm. The reason the algorithm is good about sparsity is all you do is optimize over k prime. That's the most things you do. And optimizing over k prime just involves taking a linear function and computing aj dot x, dot product with each data point. Okay? That's the only way you touch data points primarily. Now, you do touch them in the subspace power method, but I won't go into that now. So this makes it sparsity respecting. Let's see. I think that's all I'm going to say about the algorithm and the proof. We have a couple of minutes. I was hoping to run out of time, so I don't have to run through the examples, but we haven't run out of time yet. So, yeah.
I have a question. Maybe it's a naive question, but is your algorithm agnostic to the mixed, the actual weights of the mixed membership?
To the assumptions and the mixed membership. The answer is no. It would be nice to be agnostic, but at the moment, not. At the moment, delta has to be given to you. But actually, we have a later paper coming where that's not the case. But at the moment, you're not agnostic. You have to.
So you're using for each data point that has some membership, you're using its mixed membership in here. So sorry, what's
That's right. So the model has to be obeyed in the generation.
Say the what?
So you're saying, yeah, it's not agnostic in the sense that it doesn't fit the best model possible, right? Instead, it assumes there is this definite model with definite separation.
And are you estimating the mixed membership coefficients? Or
No, just the topic vectors.
And so can you estimate the mixed?
Yes. Okay. So here's a. So if you're familiar with machine learning, usually assume a prior.
Yeah.
We assume no prior.
Yeah.
So that makes the likelihood estimate inference of the weights in a way undefined. But yes, you can solve an optimization problem to say what are the best possible weights. But you don't have a prior.
And just if you were able to use that information, it wouldn't improve your learning at all?
As far as I can tell, no, because it's so unlike LDA and other things where you actually use much more detailed information about the weights in every step. We don't use it. And for that matter, it's faster in some sense, right? Because LDA, well, we don't know complexity bounds, but they're unlikely to be this fast because the number of states is enormous. But we don't know mixing times for LDAs in any case. Okay, so let me briefly, for people familiar with topic modeling, this will be very easy. Otherwise, I'm not sure I'll get through. So let me just quickly go through the examples. There are D words in our vocabulary. There are K topics. A topic is a probability vector. A stochastic process generates a document. This is LDA. We pick a hidden point Pj in the convex hull. So Pj is a mixture of topics. That's the topic of the mixed topic is the topic of the document. And you pick m words in multinomial probabilities. Now, the number of words per document is usually much lower than n and d. And that says A is sparse because A has only m non-zeros in the column. So by nature, it is sparse, right? Doxa assumes stochastically independent. Okay, now I go to another example, mixed membership communities. I'm going to deal with the general mixed membership communities model you might know is reducible to the bipartite model, which I won't go through the reduction, but the bipartite model is this. There are D people on the one side, N people on the other side. Each person on the other side has an incidence vector where Aij are 1 if and only if j knows I. And the way they are picked is you have communities, and every person in V2 is a mixed community, has a mixed community, and then picks knowing and not knowing relationship according to that. In the stochastic block model is a special case. All data are pure. Mixed membership in this way was perhaps formulated in a bunch of places, and this is one of the places. Now, the expected degree, the expected number of people you meet, you know, is much smaller than D, which is the total number. It's often just constant or logarithmic. So the graph or A is very sparse also. Not really sparse. This is basically saying that every point is really very far from K. Okay. Points are not only not in K, the data points are really extremely far from K. That's true in this example even more than topic modeling. The variances are higher here. I see this is supposed to be an example of two communities. These are the probabilities that you meet somebody. There are two communities. Also, this is two communities. And there are 4 people. Each of them is a combination of these, right? And then they picked a 0-1 matrix. A with probability of being 1 is given by P, right? And all you're given is A, and you have to find M. Not P, M. Okay. I've run out of slides.
All right.
You're allowing more questions if there are any. There aren't.
So practically speaking, how should the delta measure?
Okay, so here we assume delta is given. Now we have another paper coming where delta is delta. So delta n will be equal to something depending only on D. So you need at least D points to average to get the D vector right. And it's basically enough. That we show in a later paper. So yeah.
So for k-means, like you're saying it's a really fast algorithm. It does make an additional assumption. I guess that the centers are on a convex hole, right? Which
So the assumptions of separation, which I didn't put down,
they also have that.
we assume that.
I see.
Who has it? What did you say? I'm sorry, I didn't get
No,
it.
I'm just asking. Yeah, so that was an assumption from the original k-means papers of separation is also that they're on a convex hole.
Yeah. So the original k-means paper, we only assume distance separation between points.
Just distance separation.
Yeah.
Okay.
But here we have to assume general position. That's, they
Awesome.
cannot lie in the subspace in this for this.
Okay.
I didn't state the assumption
No,
precisely.
yeah, it's,
Yeah. But yeah, it's on the archive. You know the precise statements.